find out about plastic. I'm plastic. First, eggs. What? No cheese?
Acme presents the egg. Now, if you're expecting to find out everything you always wanted to know about cholesterol, sorry. Acme has an express policy of not whining about the things that everybody else is whining about. There seem to be about 1,093 interesting things to know about eggs. Fortunately, we only have time for the highlights. There are about 500,000 billion eggs produced every year. This must result in some mighty sore chickens. Actually, the life of a chicken isn't so glamorous. They start laying eggs at an age of 20 weeks and lay an average of 240 eggs over the next year. After that, well, it's off to the kernel, as they say in the chicken biz. Since eggs are moved quickly from the producer to the consumer, that means that it's probably possible to eat an egg for breakfast and the chicken that laid it for dinner. The egg came first, I think. Officially, the egg has 16 separate parts, but some of them are sort of subsets of each other. The outer thin white, firm white, inner thin white, and things like that. The shell is porous. That means that the eggs can dry out. This doesn't happen so quickly, so normally that's not a problem. The shell's porous nature is a problem if you have a smelly fridge, though. Store them near Limburger cheese and you'll have Limburger flavored eggs. Even though all chicken eggs are the same inside, the shell can be different colors depending on the breed of hen. Official eggshell colors are white, brown, blue, and Dr. Seuss was right, green. There's some membranes between the shell and the white, and you'll notice this when you peel a hard-boiled egg. You'll also notice this air cell at the big end. When the egg was laid, there was no air cell. As it cooled from the hen's body temperature, it shrunk a bit, pulling air in through the porous shell. The big end of the shell is more porous than the rest of the shell, so the air cell forms there. Gee, those chickens are smart. The egg white is the most interesting stuff of all. It's made of a protein, and a protein's a long chain of chemical building blocks. The egg white gets its properties from the fact that its protein is all curled up. The inner hidden components are reactive, the outer parts aren't. If you can convince that protein to open up, it'll bond in different ways. What's he talking about? Well, whipping egg white creates a new molecular structure. It's called meringue. And the egg is the only natural thing on Earth that gets harder when you heat it. In both cases, the changes are undoable. A cooled cooked egg doesn't go liquid again. This also explains two other egg mysteries. Salt and vinegar will also cause that white to coagulate. And the salt you put in the hard boiling water serves as an automatic self-patching kit if the egg cracks. The vinegar goes in the water if you're attempting a poached egg. It's almost impossible without it. In a fresh egg, the white is in two distinct components. When you crack one, the white arranges itself in two layers. Less fresh eggs do this less. The little twisty things are called collages. They help to keep the yolk centered in the egg. They work best if the egg is stored big end up, so that's the way to install them in the refrigerator. Ever since I was a kid, I've heard that eggs were candled at the grading station. I finally tried it, but instead of a candle, I used the modern equivalent, a slide projector. I expected to see something like the graphic cutaway egg. Instead, I saw nothing really. The shell was pretty interesting, but I can only see the vaguest outline of the yolk. Turns out that this is good. Anything else you see in a candled egg isn't supposed to be there in a good egg. When the egg gets old, its white thins out, and the yolk floats over to the side, casting a better shadow. At the grading station, eggs are sorted by size and quality. Eggs that are clean, have a nice appearance, a proper-sized air cell, and a properly centered yolk are called grade A. Grade A eggs are sorted into extra large, large, medium, small, and pee-wee sizes. You can buy them at the supermarket. Grades B and C go off to make everything from processed food to adhesives and shampoo. Now, by my count, that still leaves 1,086 interesting things to know about eggs. Oh, let's make that 1,085. Hard-boiled eggs spin better than raw ones. That's because the raw ones have all that stuff sloshing around. It's even been suggested that this is the best way to tell if an egg's hard-boiled or not. There's a better way. If you're in the habit of hard-boiling eggs in advance, take a pencil and write on them before you put them back in the fridge. That's the surefire way to tell if they're hard-boiled or not. Oops, 1084. There's finally an official method for hard-boiling eggs. Place the eggs in a pan, cover them with cold water. Bring this whole thing to a boil, then remove the pan, water, and eggs from the heat immediately. Set the whole thing aside somewhere. 25 minutes later, the hard-cooked eggs will be perfect. If you're making fancy eggs, you can't cool them slowly. Cooling them quickly will prevent that green sulfurous ring from forming around the yolk. If you want to know more about eggs, contact your friendly Egg Producers Marketing Board or Egg Producers Association. They'll be happy to tell you the other 1083 things.
Banana. I should get out of this business.
Most of us have a pretty vague idea of the function of air traffic control. Sure, they control the air traffic or something. The job of keeping track of several thousand planes a day seems so complex that we don't even want to think about it. Movies and TV shows often depict the job as being done by one or two people sharing an old-fashioned radar screen, chewing their nails. That's not the way it is. This is air traffic control at Pearson International Airport in Toronto. The first and second things you notice are there are a lot of controllers, and they're not up in the tower where you would expect.
35, he might get
Each controller takes care of one geographical area. The controller is responsible for all planes flying through their space. As a plane leaves a controller's area, it will be handed to another controller. Air traffic routes are well established from area to area. At lower altitudes, a vertical separation of 1,000 feet between planes is used, where the paths will cross.
Hi, Niagara, Toronto, Northwest 720 for you.
These strips represent all of the planes that the controller is monitoring. The strips contain written information about the source, destination, altitude, airspeed, equipment, and route of each plane. Even on a simple flight from Ottawa to Toronto, a pilot may talk to 15 separate controllers. The radar screens are fancier than in the movies. The older analog displays are overlaid with a digitally generated display that gives a wealth of information about each plane.
Reduce it down to, say, 30 nautical miles.
The triangle represents a plane that's the controller's responsibility.
Yes.
This asterisk is a small plane using visual flight rules at Toronto's Island Airport.
We're currently landing on the 6s.
Using a joystick and a cursor, the controller can call up additional information about a plane.
Approximately 9 miles on final, followed by another aircraft.
The display gets its information from a mixture of standard radar techniques and radio transponders that automatically send a stream of coded information from each aircraft. Air traffic has one important difference from car traffic. It can't be stopped once it's airborne. This is the flow control area. From this position, a plane on the ground as far away as San Francisco might be delayed for several minutes if it's due to land or fly past Toronto. Their purpose is to forecast the traffic demand, then develop and implement a plan to manage peak period traffic. These controllers monitor air traffic through, to, and from the Toronto region. Once an aircraft is safely guided to the airport, it's handed over to these folks. The controllers in the tower handle all flights on close final approach and all traffic on the ground. That includes taxiing planes as well as service vehicles. The tower has conventional radar displays as well as airport surface detection. This radar shows all runways, taxiways, and terminals. Nothing on the ground budges without clearance from the tower. The conventional radar is showing a 30-mile radius. Again, the triangles represent airborne planes. When the plane lands, the triangle disappears. The tower is in constant communication with all ground traffic and the other controllers. For instance, during our visit, this flight to Chicago was being held on the ground because this flight en route overhead to Chicago was running late. We were given permission to photograph all of this during a slack time of the day. During airport peak traffic periods, distractions to the controllers aren't allowed. Finding out the scope of the air traffic system cleared up a lot of the mystery of the delays you sometimes experience when flying. While you may be simply worried about your arrival time in Boca Raton, the controllers have to concern themselves with hundreds of factors that will affect your flight, right down to the location of the catering trucks at your stopover point. Sometimes an intense job, but never a boring one. It's hard to remember the moment that everything in our lives became plastic. In the 1960s, the word plastic conjured up notions of cheapness and vulgarity. And then we grew up, and so did plastics. Today's plastics make most products lighter, stronger, cheaper, and in the case of electrical things, safer. Plastics can be made with almost any characteristics: hard, brittle, soft, transparent, opaque. As well, they can be made to melt and flow precisely to create almost any one-piece shape. Even though plastic manufacturing has become a big business, there's nothing to modern plastics that goes too far beyond high school chemistry. Aging hippies will be distressed to hear this, but plastic is organic. The front bumper of your car and the wheels on your baby buggy all trace their roots back to tiny plants and animals that died millions of years ago. The basic building blocks of plastics are hydrocarbons. The carbon atom has 6 electrons. Now, according to the chemistry you hated in high school, electrons will arrange themselves in bands according to the rules of 2, 8, and 8. Since carbon only has 6 electrons, they arrange in bands of 2 and 4. Now, it's important to note that the carbon atom is electrically balanced. It's got 6 protons in the nucleus and 6 electrons in orbit. The outermost orbit is called the atom's valence band. Carbon properly fills its first band with 2 electrons, but it only has 4 available to place in the next one. By the 2-8-8 rule of valence bands, it needs 4 more electrons. Now, carbon can't simply capture 4 more electrons because it's already electrically neutral. It can solve its tiny atomic conundrum by forming a so-called covalent bond with 4 hydrogen atoms. Hydrogen only has 1 electron, and by the rules of valency, this first shell should have 2. So given a chance, hydrogen and carbon will happily hang around together in a pattern like this. This is the gas methane. To go beyond methane will get graphically messy with all of these orbits and shared electrons. So we're going to switch to a more standard chemistry notation. Now, heat and pressure can be used to force the bonds open and make other hydrocarbons, all using covalent bonding to fill those outer valence bands. This one's octane. This is paraffin. You might know it as candle wax. Now the pictures are getting smaller because the number of bonds is increasing. In real life, the atoms are the same size, but the characteristics of the material change. The methane molecule is small. It can wander around by itself, so it does. It exists as a gas at normal temperatures and pressures. Octane has more baggage, and it exists as a liquid. Paraffin, well, you get the picture. The characteristics of a substance tend to take on the properties of the arrangement of their molecules. Plastics are made from long repeating chains of hydrocarbon molecules called polymers. Poly simply means many. Plastic is from an old Greek word meaning capable of being molded. Your basic plastic polymer is usually a long strand of bonded atoms that looks like a molecular plate of spaghetti. Depending on the exact bonding arrangement, the final polymer might be rigid, rubbery, or liquid. Plastics divide into two main groups, thermoset and thermoplastic. The thermosets are like cake batter. Once you transform them, they become rigid and they can't ever revert. Fiberglass resin is the most common thermoset. Most of the plastics that you have in your house and your driveway are thermoplastics. Thermoplastic can be softened to flow and cools back to rigidity. Some thermoplastics have long flowing structures with a broad melting range, like butter. Others have a crystalline structure, like ice, and a sharp melting point to match. Thermoplastics can be melted and remelted as often as you like without undergoing any change. The added heat temporarily loosens those bonds, allowing them to slip. A plastic car bumper can be shredded and remolded to make another one. So can a plastic bag. And your watering can probably started life as a milk jug. Plastics that have been carefully created to match a specific part or product are known as engineering plastics. This is the General Electric plastics plant in Cobourg, Ontario. Although GE makes various engineering plastics that find their way into compact discs, airplanes, cookware, cars, and tennis shoes, this plant specializes in ABS, made from acrylonitrile, butadiene, and styrene. You probably met ABS pipe under the sink drain, but slight adjustments to its manufacture can create hundreds of varieties with carefully controlled characteristics. Raw materials are obtained from petroleum refiners and arrive at the plant by rail and tanker. By controlling the temperature, pressure, and time, molecules of plastic are carefully built to exact specifications. Polymers of ABS can be created that have specific melting points, structures, and strength. Plastic's also popular in manufacturing because its color is integral. Not only will the final product not require painting, but any dents or scratches will be the same color as the surface. Color is very important to most manufacturers. Here, a sample of car interior is being checked in the lab to ensure that it looks the same under various lighting conditions. Plastic travels through the plant through pipes and ducts. This hopper allows access to the polymer soup for the addition of pigment and lubricants. The molten plastic is extruded into long strands and cooled in a trough of water. This shaker separates any pellets that are too large. Thermoplastic travels from the manufacturer as pellets in bags, boxes, and tanker trucks. Plastic is usually extruded like pipe and rain gutters or injection molded. Your first experience with injection molding was probably in a model airplane kit. Nowadays, the molds are designed on a computer and created by hand and fancy computer-driven machinery. Molten plastic is forced into the mold at high pressure and out pops the part. Well, this is a nice montage, but depending on the size and design of the part, molding often takes a minute or so. The molder has to know the molecular characteristics of the plastic being used because the exact amount of pressure and the molding temperature will affect how the plastic flows and how much it shrinks while it cools. The molding pressure also has an effect on the final density of the part. Injection molding of modern plastics has gone a long way beyond the model airplane kit. Injection molded plastic parts are now the preferred precision parts in most machinery. Modern plastic parts are engineered from the molecule on up. For instance, your car grille will shatter easier than the bumper in front of it because the grille had to use a plastic that flowed through a more intricate mold. Acme thinks it's time to acknowledge plastic as a proud member of humanity's good things. After all, it's organic. I'm pretty proud of that item on plastics. I think I managed to cover up my dismal lack of understanding of chemistry pretty well. Actually, I had a lot of help from the folks at GE Plastics. There was so much to cover, though, I had to leave out a couple of my favorite bits of plastic trivia. The first plastic dates back to 1856, celluloid. It was used to replace ivory for making things like combs, piano keys, and billiard balls. The second plastic came along in 1909, Bakelite. It was used for pot handles and radio cabinets. In the next program, we're going to devote the entire half hour, well, you know, for broadcast, a half hour is actually 24 minutes. It's a metric, I think. But we're going to devote that entire half hour to the modern mechanical methods of making music. Next, Peter Piper picks a pack of pickled peppers, probably.